Hello and welcome to the following revision session for AQA A-Level Physics Paper 3, looking at our Astrophysics option concerning questions regarding stars. So if we've been successful and we've learned in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for AQA A-Level Physics. So how should you be preparing for this revision session? When you complete your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your work and answers to the questions in the revision session. When doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for AQA A-Level Physics Paper 3? Well, the first step is to learn the key facts. Use revision guides, class workbooks, prep notes and then textbooks to learn the key ideas of the course. Then test yourself. Use things like Caboodle, Seneca, knowledge checkers to quickly test your own knowledge. Finally, practice exam style questions with exam practice books, homework books, study books, additional workbooks to answer exam questions and mark your own work. So learn the key facts, test yourself and then practice exam style questions. So what are the key facts concerning stars? Well, we have classification by luminosity. So apparent magnitude is a measure of how bright a star appears from Earth. The brighter the star, the lower the magnitude value. We use a Hipparcos scale. Now the difference of one magnitude on this scale is a brightness ratio of 2.51. This scale is logarithmic, with the dimmest visible stars having an apparent magnitude of 6. Now this is subjective and affected by the atmosphere and background light. Now absolute magnitude is the apparent magnitude a star would have if it was placed 10 parsecs away from the Earth. This leads to our relationship of m minus m equals 5 log d over 10, where d is our distance in parsecs. Now the conversion between parsecs and a light year is that 1 parsec is 3.26 light years. We can also have classification by temperature. Firstly, we know the Wien displacement law is the maximum wavelength times by the absolute temperature is equal to 2.9 times 10 to the minus 3. This helps estimate the surface temperature of stars based on the peak wavelength of emission. Our Stefan-Boltzmann law is the power of a star is equal to sigma a t to the 4, but we have our blackbody assumption with this, that a star is modelled as a perfect blackbody. It absorbs and emits all radiation. The inverse square law applies to the intensity and the distance to an object. So intensity is proportional to 1 over to the separation of the object squared, and we use this to estimate the star's luminosity, radius and temperature. Now in terms of classification by temperature, the hydrogen Balmer lines appear in a star spectrum only if the electrons in the hydrogen atoms are in our second energy level. So this leads to classification by stellar spectral class, where we have our spectral class of O, A, B, F, G, K and M, our intrinsic colours of each classes, the surface temperature of those classes of objects, and the prominent absorption lines found in the spectra of those stars. Now in terms of the Hertzsprung-Russell diagram, our Hertzsprung-Russell diagram structure is that the graph is plotted of luminosity or absolute magnitude against the temperature of spectral class. Our temperature decreases from the right to the left. The main regions are our main sequence, the long stable life of a star, giants and supergiants, the large bright cooler stars, and the white dwarfs, which is the hot but dim stars. The scales are absolute magnitude from minus 10, which is very bright, to plus 15, which is very dim. The temperatures go from 50,000 Kelvin, which is a hot blue object, to 2,500 Kelvin, which is a cool red object. Our spectral classes are O, B, A, F, G, K and M, from the hottest to the coolest. Now the sun's position on a Hertzsprung-Russell diagram is located on the main sequence section at around 5,800 Kelvin and an absolute magnitude of plus 4.8. Now the standard stellar evolution path is from protostar to main sequence to red giant to white dwarf for sun-like stars. Now a supernovae is important, as the type 1a supernovae are used as standard candles to measure astronomical distances. The definition of a supernova is a rapid increase in the absolute magnitude of an object, usually caused by a catastrophic collapse or fusion runaway event, and is used to support evidence for dark energy and the accelerating universe. Neutrons are formed by the collapse of massive stars. They're extremely dense and composed mostly of neutrons. The radius of a neutron star is about 10 kilometers. Black holes are collapsed that lead to infinite density, where the escape velocity is greater than the speed of light. Now the center of most galaxies are thought to contain a supermassive black hole. Gamma ray bursts are emitted during the collapse of a massive star into a neutron star or a black hole. You must be able to understand and sketch the type 1a supernova light curve with a rapid increase in brightness up until -19 absolute magnitude, followed by a gradual decline, and we know that the energy outputs compared to the sun's total energy output. The Schwarzschild radius of a black hole is equal to 2gm over c squared. So let's have a look at some general check questions regarding stars. So, a nearby star has an angle of parallax of 1.39 times 10 to the minus 4 degrees. Calculate the distance to the star. The average radius of the Earth's orbit is 1.5 times 10 to the 11 meters. You must convert the angle to radians, so it's 1.39 times 10 to the minus 4 times by pi over 180, which is 2.42 times 10 to the minus 6 radians. The distance is therefore the radius over the angle, so we get 6.18 times 10 to the 16 meters. Proxima Centauri has an angle of parallax of 0.77 arc seconds. Calculate the distance to Proxima Centauri in parsecs. As a shortcut, we can say distance in parsecs is equal to the 1 over the angle of parallax in arc seconds. So it's 1 over 0.77, 1.3 parsecs. The star Sirius has an apparent magnitude of minus 1.46, whilst the star Vega has an apparent magnitude of 0.03. Which star appears brighter in the night sky, and by what factor is it brighter? So we can tell straight away that Sirius is the brightest star, as it has a more negative apparent magnitude. To find the difference in brightness, you've got to do 2.51 to the difference in their magnitude values. So it's 2.51 to 1.49, which is 3.39, so Sirius appears 3.93 times brighter than Vega. The star Procyon has an apparent magnitude of 0.34 and is located 3.5 parsecs from the Earth. Calculate its absolute magnitude. We've got to use the equation m minus m equals 5 log d over 10. We then rearrange it to make big M the absolute magnitude of the subject. So it's going to be m minus 5 log d plus 5 when you're working through the laws of logs. We then pop in the values. As you can see, we get 2.62. A star has an apparent magnitude of 4.5 and an absolute magnitude of 1.5. Determine how far away it is in parsecs. Once again, we use m equals m minus 5 log d plus 5. So we've just rearranged our equation, used the information worked out last time. We pop in the values and we get d is going to be equal to 10 to the power of 1.6, which is 39.8 parsecs. Two stars, star A and star B, have absolute magnitudes of minus 3 and 2 respectively. How much more luminous is star A compared to star B? So we do 2.51 to the power of the difference in the magnitude value. So 2.51 to the power of 5, which is 100. So star A is 100 times more luminous than star B. A separate variable star has an apparent magnitude of 6. It's been determined through its period luminosity relationship that has an absolute magnitude of minus 2.5. Calculate its distance from the Earth in parsecs. Once again, we use our equation m minus m equals 5 log d minus 5. Pop in all the values, we then get d is equal to 10 to the power of 2.7, so therefore we get 501 parsecs. The graph shows how the radiation intensity varies with wavelength of star X and star Y. The surface temperature of star X is Tx and the surface temperature of star Y is Ty. Which star has the highest surface temperature and how do you know? Tx must be greater than Ty, because the peak intensity for star X is at the shorter wavelength. The star Rigel in the constellation Orion is measured to have a surface temperature of 12,000 Kelvin. The Sun has a surface temperature of 5,800 Kelvin. Suggest how Rigel's peak wavelength will differ to that of the Sun. Rigel's peak wavelength will be shorter than the Sun's because Rigel has a higher surface temperature than the Sun. How does a black body emission curve change as the temperature of the body increases? The intensity at all wavelengths will be higher and the peak wavelength will shift to the shorter wavelengths. Explain how a black body emission curve can be used to determine the surface temperature of a star. So you determine the peak wavelength of emission by finding the peak of the curve. Then we use the Wien displacement law of lambda max times by t equals 2.9 times 10 to the minus 3 to determine the surface temperature of the star. A star emits most of its radiation at a wavelength of 450 nanometers. Calculate the surface temperature of the star. We know lambda max times by t is 2.9 times 10 to the minus 3. We rearrange it to make t the subject and put in the numbers 6,440 Kelvin. A star has a surface temperature of 5,800 Kelvin and a radius of 7 times 10 to the 8 meters. Calculate its luminosity. We know that the surface area of this photon sphere is 4 pi r squared. We then can say the luminosity is equal to sigma a t to the 4, because luminosity and power are going to be the same thing. We then pop in all the values. Remember, we've worked out the area to be 4 pi r squared. We then pop in the values and we get 3.93 times 10 to the 26 watts. The Sun has a surface temperature of 5,800 Kelvin and a radius of 6.96 times 10 to the 8 meters. What surface temperature would a star have if it had a radius of 9.42 times 10 to 7 meters with the same luminosity as the Sun? So what we can do is we can ratio the values. So we can say, because r is equal to the square root of L, the luminosity, over 4 pi epsilon sigma t to the 4, that the temperature is going to be the fourth square root of the radius of the Sun squared times by the temperature of the Sun to the power of 4 over the radius of the star squared. We pop in all the values and we get 16,000 Kelvin. Sirius A is a main sequence star and Sirius B is a white dwarf star. Sirius A has a surface temperature of 9,800 Kelvin and produces electromagnetic radiation with a peak wavelength of 300 nanometers. Sirius B has a luminosity of 9.4 times 10 to 24 watts and produces electromagnetic radiation with a peak wavelength of 115 nanometers. Estimate the temperature of Sirius B. Well, we can ratio them and say Ta times by lambda A is equal to Tb times by lambda B. So we then can rearrange it to make Tb the subject, pop in all the values, we get 26,000 Kelvin. A star has a luminosity of 2 times 10 to 30 watts and a surface temperature of 8,000 Kelvin. Calculate its radius. We rearrange our equation to say r is equal to the square root of the luminosity over 4 pi sigma t to the 4. Pop in all the values, we get 8.3 times 10 to the 9 meters. Sirius A is a main sequence star and Sirius B is a white dwarf star. Sirius A has a surface temperature of 9,800 Kelvin and produces electromagnetic radiation with a peak wavelength of 300 nanometers. Sirius B has a luminosity of 9.4 times 10 to 24 watts and produces electromagnetic radiation with a peak wavelength of 115 nanometers. Estimate the radius of Sirius B. So we can say Ta lambda A equals Tb lambda B. We use this to work out the temperature of Sirius B to be 25,565 Kelvin. We can then say r is equal to the square root of L over 4 pi sigma t to the 4. We then pop in all the values and we get 5.6 times 10 to the 6 meters. Two stars, star A and star B, have the following properties. Star A has a radius of 2 times 10 to 9 meters and a temperature of 3,500 Kelvin. Star B has a radius of 1 times 10 to 9 meters and a temperature of 7,000 Kelvin. Determine how much more luminous star B is compared to star A. So we use the equation L is equal to sigma 4 pi r squared t to the 4. So sigma and 4 pi will cancel out. So the ratio LB to LA is r squared b t to the 4b over r squared a t to the 4a. Pop in all the values and we get 4.6. So Sirius star B is 4.6 times more luminous than star A. A red giant has a radius of 5 times 10 to the 10 meters and a luminosity of 2.5 times 10 to 30 watts. Determine the peak wavelength of its emission spectrum. So we can work out the luminosity by saying sigma 4 pi r squared t to the 4. We can rearrange that and make t the subject. We pop in the values, we get t to be 6,120 Kelvin. We can then say lambda max is 2.9 times 10 to the 3 over minus 3 over this temperature. Pop it all in, we get 4.74 times 10 to the minus 7 meters. The spectral class system orders stars by temperature from the hottest to the coolest. List the spectral types in order, starting with the hottest stars, and state the approximate temperatures for O and M type stars. So the spectral order is O, B, A, F, G, K and M. O type stars have a temperature above 25,000 Kelvin, whilst M type stars are below 3,500 Kelvin. A star has a surface temperature of 5,800 Kelvin. Identify its spectral class and describe the expected characteristics of its spectrum. A star with a surface temperature of 5,800 Kelvin falls into the G spectral class. It'll have weak hydrogen lines, strong ionized and neutral metal lines, and a yellow colour. An astronomer observes the following star. Star X displays strong hydrogen Balmer lines and appears white. Identify the spectral class of star, explain your reasoning based on their spectral features. The strong hydrogen Balmer lines indicate abundant hydrogen transitions. The white colour suggests a hot star but not the hottest, so these characteristics of A-type stars which have strong Balmer lines due to their optimal excitation of hydrogen electrons from the n=2 energy level. Star Y shows weak hydrogen lines but strong molecular bands and appears red. Identify the spectral class of the star. Explain your reasoning based on their spectral features. Weak hydrogen lines and strong molecular bands imply a cooler star where molecules can form. The red appearance confirms a low surface temperature, so these are traits of an M-type star which are the coolest and have most prominent molecular absorption features. Explain if Balmer lines are observed at low temperatures. At low temperatures, most hydrogen atoms have electrons in the ground state n=1. Since Balmer line requires transitions to or from the n=2, these lines are very weak or absent. Explain if Balmer lines are observed at intermediate temperatures. At intermediate temperatures, a significant number of the hydrogen atoms have electrons in the n=2 state. This leads to strong Balmer absorption lines, so A-type stars with this temperatures exhibit the strongest Balmer lines. Explain if Balmer lines are observed at high temperatures. At high temperatures, many hydrogen atoms become ionized, so they have lost their electrons. Without electrons in bound states, the Balmer absorption lines will weaken. A star spectrum shows strong Balmer lines along with moderate ionized helium lines. Determine the spectral class of the star and justify your answer. Strong hydrogen Balmer lines suggest a temperature between 7,500 and 10,000 Kelvin, which is characteristic of A-type stars. The ionized helium lines indicate a hotter temperature typically found in B-type stars. Now, A-type stars have the strongest Balmer lines, but B-type stars show both Balmer lines and ionized helium lines. So since the spectrum contains moderate ionized helium lines alongside strong Balmer lines, the star is likely a B-type star. Explain why the Balmer series of absorption lines is only observed in the visible spectrum, whilst other series are not. The Balmer lines correspond to electron transitions with a second energy level, n=2. The energy differences between these levels results in emissions of photons in the visible light spectrum. The Lyman series involves transitions of the first energy level, n=1, resulting in higher energy photons in the UV. The Paschen series involves transitions with the third energy level, n=3, resulting in lower energy photons in the infrared region. So therefore Balmer series is observed in the visible spectrum, whilst other series are observed in the non-visible spectrum, the ultraviolet and infrared regions. The luminosity axis of a Hertzsprung-Russell diagram has a logarithmic scale. What's the reason for this? Well, the range of luminosities of the star is very large, indicated by the logarithmic absolute magnitude scale. Explain why most stars are found on the main sequence of the Hertzsprung-Russell diagram. Most stars are found on the main sequence because this is the stage where the stars spend the majority of their lifetimes. During this phase, the stars are in equilibrium, fusing hydrogen into helium cores. A star is observed to have a surface temperature of 10,000 Kelvin and a luminosity 100 times that of the Sun. Determine its position on the Hertzsprung-Russell diagram and identify its likely spectral class. A star with a surface temperature of 10,000 Kelvin and a luminosity 100 times that of the Sun will be located on the upper part of the main sequence. The spectral class of the star is likely to be B. Stars in this class are hot and blue, with temperatures from 10,000 to 30,000 Kelvin. For the following information, plot the star's position on a simplified Hertzsprung-Russell diagram and identify its evolutionary stages. Star A has a temperature of 3,000 Kelvin and a luminosity 1,000 times that of the Sun. We'd find it goes there. With a temperature of 3,000 Kelvin and a luminosity around 1,000 times that of the Sun, it will be located in the upper right hand corner, indicating to be a red giant. Star B has a temperature of 20,000 Kelvin and a luminosity of 0.1 that of the Sun. This will be found here. With these factors, it will be in the lower left, indicating it's a white dwarf. Star C has a temperature of 6,000 Kelvin and a luminosity 1 times that of the Sun, so it will be found round here. So it will be very similar to that of the Sun. It will be on the main sequence, so it's a main sequence star. An astronomer observes a Type 1a supernova in a distant galaxy with an apparent magnitude of +11 at its peak brightness. At its peak, it's known that the Type 1a supernova has an absolute magnitude of -19, so that the galaxy is about 10 megaparsecs away. We use the equation m minus m equals 5 log d over 10. We once again rearrange it to get d to be the subject. D is equal to 10 to the power of 10 to the 6, so therefore it is 10 megaparsecs. Describe the light curve of a typical Type 1a supernovae and explain its significance in determined distances in the universe. The light curve of a typical Type 1a supernova shows a rapid rise to a peak brightness, followed by a gradual decline. The peak luminosity is very consistent among Type 1a supernovae, making them excellent standard candles for measuring cosmic distances. By comparing the observed brightness with the known absolute magnitude, astronomers can calculate the distance to supernovae and consequently the distance to its host galaxy. Gamma-ray bursts are thought to be associated with the collapse of supergiant stars to form neutron stars or black holes. Compare the energy output of a typical GRB with the total energy output of the Sun over its entire lifetime. A typical gamma-ray burst releases about 10 to the 44 joules of energy in a few seconds. In comparison, the total energy output of the Sun over its entire lifetime is approximately 10 to the 44 joules. This means a single GRB can release as much energy in a few seconds as the Sun will emit over its entire 10 billion year lifetime. A neutron star has a mass of 2 times 10 to 30 kilograms and a radius of 10 kilometers. Calculate its density and compare it to the density of an atomic nucleus. We know that density is mass over volume, where the volume is 4 over 3 pi r cubed. We pop in all our values, remembering that 10 kilometers just be converted into meters, and we get our answer to be 4.77 times 10 to 17 kilograms per meter cubed. Now the density of a neutron star is about twice that of an atomic nucleus. Calculate the Schwarzschild radius for a supermassive black hole with a mass of 10 to the 9 solar masses. We know the mass of the Sun is 1.99 times 10 to 30 kilograms, so we can then say the mass of this black hole is 1.989 times 10 to 39 kilograms. We know the Schwarzschild radius is 2 gm over c squared, so we pop in the values and we get 2.95 times 10 to 12 meters. Calculate the Schwarzschild radius of a supermassive black hole with a mass of 4 times 10 to 6 m, like the one at the centre of the Milky Way. Once again, we convert our mass into that of from the solar masses into the mass in kilograms, so we get 7.96 times 10 to 36 kilograms. We then use the Schwarzschild radius of 2 gm over c squared to get our answer to be 1.18 times 10 to the 10 meters. Let's have a look at some questions regarding stars. An exoplanetary system is discovered by a European observatory and reported to lie at a distance of 4.8 parsecs from the Earth. A popular science article about the discovery later describes the system as over 150 light years away, leading to confusion among readers. A physics student curious about the discrepancy checks the observatory data and wonders whether the journalist has made a mistake or used an alternate measurement system. They begin comparing the two distance units to resolve the inconsistency. Explain what is meant by a parsec, including how it relates to astronomical observation. Based on the observatory's distance value, assess whether the claim made in the article is reasonable. Support your answer with appropriate reasoning. Then suggest one reason why astronomers might prefer to use parsecs over light years in research publications, despite light years being more widely understood by the public. So pause the video now, and then unpause the video when you want to go through your answer. Right, a parsec is the distance at which a star would have a parallax angle of 1 arcsecond when the Earth moves 1 AU around the Sun. It's based on the triangulation using the Earth's orbit as a baseline, which you may want to draw a diagram for. 1 parsec is 3.26 light years, so they're directly related to parallax measurements. We can therefore use our conversion factor to say that's 15.65 light years. The article claims it's over 150 light years, an order of magnitude larger than the correct value. So this suggests the journalist slightly confused parsecs with light years or made a unit conversion error. So the article's distance is not consistent with the observatory data and is incorrect. Now, parsecs are directly tied into observational techniques, especially used in parallax measurements, making them more convenient for scientific use. Light years require additional conversions and are more conceptually intuitive but less practical for these calculations. So scientists will use parsecs for standardization across professional literature, even if public communication uses light years for familiarity. An amateur astronomer based in a large city reports that they're only able to see stars with an apparent magnitude brighter than 3.5, even when using a high-quality telescope. They attempt to compare this observation with published data from the Hipparchus satellite, which includes stars with an apparent magnitude as faint as 9. The astronomer notes that from darker rural locations, they were able to observe stars with magnitude as faint as 6 using the same equipment. Suggests two possible reasons why the astronomer is unable to observe fainter stars in the city, and explain the role of apparent magnitude scales in supporting this observation. Calculate how many times brighter a star of 3.5 apparent magnitude appears than a star of magnitude 6. The astronomer suggests the Hipparchus magnitude scale might not reflect true brightness in the way people perceive it with the eye. Discuss and evaluate this claim, referring to how apparent magnitude relates to both physical intensity and human perception. So pause the video now, and then unpause the video when you want to go through your answer. Right, light pollution in cities causes background brightness obscuring dimmer stars. The atmospheric scattering or pollution reduces the contrast between the faint stars and the sky. So the apparent magnitude is a logarithmic scale, so even small numerical differences represent large differences in brightness, so a cutoff at 3.5 compared to 6 is very significant. To work out our difference in brightness, we do 2.51 to the difference in the magnitude, so it's 2.51 to the power of 2.5, which is 10. So a magnitude 3.5 star appears 10 times brighter than a magnitude 6 star. The apparent magnitude is based on measured intensity, not a subjective visual impression. The human perception of brightness is non-linear and is affected by background light and adaptation. The scale is logarithmic to reflect how the human eye perceives brightness changes, but is still based on quantifiable light intensity. So the claim has some truth for everyday experience, but apparent magnitude is scientifically defined and a consistent system for comparing star visibility under ideal conditions. An international amateur astronomy organisation launches a citizen science project asking volunteers to measure star visibility in different distances by comparing what they can see with data from the Hipparchus star catalogue. 2 observation sites are selected. Site A, in a rural national park, reports the faintest stars visible to the unaided eye is listed in the catalogue as having an apparent magnitude of 5.8. Site B, a town centre, reports the faintest visible star has a magnitude of 3.3. One participant suggests the town site must be at least 5 times less bright overall than the rural site, based on their experiences. The project team is unsure whether this statement is accurate or supported by the data. Explain how the concept of apparent magnitude helps observers classify stars' visibility, and describe what the values of 5.8 and 3.3 indicate about the 2 sites. Critically assess the participant's suggestion that Site B is at least 5 times less bright than Site A. Support your answer with relative reason or analysis. Then discuss one limitation of using apparent magnitude as a tool for comparing sky brightness between different locations, and suggest how this limitation might be addressed in observational projects. So pause the video now, and then unpause the video when you want to go through your answer. We know in our first one that apparent magnitude is a logarithmic measure of brightness as seen from the Earth. The higher magnitude values indicate fainter stars, so Site A allows fainter stars to be seen, indicating a darker sky and less light pollution than Site B. The difference between the two of them is 2.51 to 2 to the 2.5, which is 10. So Site A allows stars roughly 10 times fainter to be seen. Participants claim that Site B is at least 5 times less bright, underestimates the actual difference. So the claim is incorrect based on a quantitative comparison. Site B is in fact 10 times less sensitive to faint light, not 5. Finally, apparent magnitude measures star brightness but doesn't account for atmospheric or observational conditions like cloud cover, humidity, or observer eyesight. The results are subjective unless supported by a calibrated equipment. Now, this could be improved by using photometers or providing reference star charts for participants to standardize visibility assessments. A space-based telescope collects photometric data for a nearby cluster of stars. One of the stars in the sample is classed spectroscopically as a type G main sequence star, similar to the Sun, and it's expected to have an absolute magnitude of approximately 4 plus 4.8. The apparent magnitude measured for this star is plus 9.3, but the distance to the star based on parallax is later independently confirmed to be 60 parsecs. A student analysing the results notices that the apparent and absolute magnitudes do not seem to match the expected distance, and wonders if the telescope's reading is flawed or the assumption about the star's classification is incorrect. outline the physical meaning of absolute magnitude and explain how it differs from apparent magnitude, analyze the data provided and determine whether the photometric data and the parallax distance are consistent, justify your conclusion. Suggest one possible astrophysical or observational reason why the apparent magnitude measurement might not agree with the parallax-derived distance, even if both methods are accurate. So pause the video now, and then unpause the video when you want to go through your answer. The absolute magnitude is the apparent magnitude a star would have if it was placed at a distance of 10 parsecs from the Earth. It is a measure of the intrinsic brightness of a star. The apparent magnitude depends on the star's intrinsic brightness and its distance from the Earth. Now, when we use m minus m equals 5 log d over 10, we pop in the values, and therefore we get the value to be 3.89. Now, it says it's 4.5, it is in fact 3.9, suggesting the distance or the classification is likely incorrect, or a measurement of apparent magnitude is being affected. Now, the apparent magnitude could be affected by something like interstellar dust causing extinction and making the star look dimmer. The star may be older or larger or smaller than a typical G-type main sequence star, or the telescope or the instrument might have a calibration error which might cause inaccurate readings to be collected. A team of astronomers are studying a newly discovered star cluster in a nearby dwarf galaxy, and they observe that several stars do not match expected trends in spectral classification. One star in particular, KX72, shows strong Balmer absorption lines despite the spectral classification suggesting a relatively low surface temperature. The team cross-references the spectrum with the standard OB-AFGKM class and notes that the stars with the strongest Balmer lines are typically classified as A-type stars with surface temperature on 9,500 Kelvin. However, KX72 is much redder than expected for an A-type star, and its temperature-derived photometry is closer to 5,800 Kelvin, more typical of a G-type star. Explain how a star's spectral class relates to its surface temperature and colour. Include the role of atomic transitions in producing absorption lines in your answer. Use your knowledge of the hydrogen atom. Explain why the Balmer line absorption lines are only visible under specific temperature conditions. Then evaluate two possible reasons why star KX72 might show unexpectedly strong Balmer lines despite its lower temperature. Support your reasoning using astrophysical principles. So pause the video now, and then unpause the video when you want to go through your answer. The spectral class is based on the star's surface temperature, with O-type being the hottest and M-type the coolest. Colour follows temperature. Blue stars are hotter, red stars are cooler. The absorption lines are produced when the photons are absorbed by electrons transitioning to higher energy levels. So particular lines appear dependent on where the atoms are in the right excitation states with their electrons. Balmer lines are transitions involving the n equals 2 energy level of hydrogen, so for absorption to occur the electrons must be in the n equals 2 state already. This state is only significantly populated at certain temperatures, making Balmer lines the strongest in A-type stars. Now, possibility 1 is that the star is part of a binary system with a hotter companion contributing some strong Balmer lines. This could result in a composite spectrum of the two, misleading the classification. Another possibility is that it may have an extended atmosphere or surrounding shell at a suitable temperature for Balmer absorption. Now, both explanations involve concepts where absorption does not directly correspond to the star's surface temperature, which is what the lines would show. Astronomers surveying a group of stars in the galactic halo note an unusual pattern. Many of the stars show weak absent Balmer absorption lines despite their blue colour and high surface temperatures. A student reviewed the results is surprised. They recall that Balmer lines are usually strong in blue stars and decided to investigate further by comparing the spectra with reference stars across the star smellers classification. Describe how Balmer absorption lines arise in the star spectrum. Explain the conditions under which these lines are most prominent. Using your understanding of atomic structure and thermodynamic population of energy levels, explain why very hot stars show weaker Balmer lines despite their high temperature. Suggest how astronomers could use the presence or absence of Balmer lines in conjunction with colour to distinguish between stars of similar appearances with different underlying properties. So pause the video now, and then unpause the video when you want to go through your answer. We know that Balmer lines are due to electrons transitions in the hydrogen involving the n equals 2 level. Absorption occurs when the electrons absorb photons and move to higher energy levels. For these lines to appear, a significant number of electrons must already be in n equals 2. This occurs most effectively at around temperatures of 9,000 to 10,000 Kelvin, typical of A-type stars. In very hot stars, the temperature is too high for many hydrogen atoms to remain neutral. Hydrogen becomes ionized, meaning electrons are no longer bound in atoms. With fewer electrons in bound states, the absorption lines become weak or absent. Even if some atoms remain neutral, most electrons are in the higher energy levels, not n equals 2. So therefore, despite the high temperatures, the Balmer lines are weaker due to ionization and them not being in the n equals 2 state. The colour will give a general idea of surface temperature, like blue is hot, but not detailed spectral properties. A star with strong Balmer lines and blue colour is likely to be an A-type star. However, blue stars without the strong lines are likely to be O-type or hot white dwarfs. Comparing the Balmer line strengths and profiles alongside the colour allows astronomers to distinguish spectral class, temperature, and ionization state. Astronomers observe 5 stars in a young open cluster. Their spectra are carefully measured to determine apparent colour, estimate the surface temperature, and the strength of Balmer absorption lines. The student below is analysing the following simplified data. Explain why the strength of hydrogen Balmer lines varies with stellar surface temperature, referring to atomic transitions in your answer. Compare the data in the table and identify which star is most likely to belong to A spectral class. Justify your answer using evidence from the data. Stars A and C both show weak Balmer lines, despite large differences in surface temperatures. Explain why weak lines arise in each case, and evaluate why these lines arise for different physical reasons. So pause the video now, and then unpause the video when you want to go through your answer. Balmer line absorption due to electron transitions in hydrogen star from the n equals 2 level. At a moderate temperature, many electrons occupy the n equals 2 level, enabling strong Balmer absorption. At lower temperatures, most electrons are in the ground state, so fewer transitions involving N2 occur. At very high temperatures, hydrogen becomes ionized and there are fewer neutral atoms available for absorption. Star B has a surface temperature of 10,000 Kelvin, typical for an A-type star. It also shows strong Balmer lines consistent with A-type classification. So Star B is most likely the A-type star based on both temperature and spectral features. In Star A, the high temperature causes ionization of hydrogen, reducing the number of atoms with electrons in the n equals 2 state, so you have weak lines. In Star C, most electrons in the n equals 1 ground state, so very few can absorb Balmer photons, weak lines. Though both stars show some weak Balmer lines, their causes differ, high temperature versus low temperature. So this shows the line strength does not simply scale with temperature, it depends on how many atoms have electrons in the right state, which is important to indicate why you interpret the spectral lines in context. Different processes can produce similar observational features. An astrophysics research group is studying the long-term brightness and temperature changes in a sun-like star. They collect data over decades and trace the movement on a HR diagram. The students suggest that as the star evolves, it gets hotter and brighter in every stage, as this will match the idea of becoming more energetic over time. Using the data and the structure of a HR diagram, describe the path of the star from main sequence through to the white dwarf stage. Explain the physical processes that driving the changes in temperature and luminosity at each stage of the star's evolution. Evaluate the student's statement in the context of the HR diagram and data. Is it accurate to describe the stars becoming hotter and brighter throughout its evolution? So pause the video now, then unpause the video when you want to go through your answer. The main sequence is a star in hydrostatic equilibrium undergoing hydrogen fusion in the core, and is located about 5,800 Kelvin with a plus 4.8 magnitude. In the red giant phase, the star expands and the surface cools to 3,200 Kelvin, but the luminosity increases significantly due to increased surface area. It shifts up and to the right on the Hertzsprung-Russell diagram. The helium flash, where the core contracts and heats, the outer layers shrink, and the temperature rises with a small increase in luminosity. There's a slight shift leftward and upward. In the planetary nebula, outer layers are ejected, revealing a hot core which is small and luminous, so it moves left and downward. In the white dwarf part, it's small, hot and dim. It's positioned to the bottom left of the Hertzsprung-Russell diagram with a high temperature, low luminosity. On the main sequence, the fusion of hydrogen to helium in the core sustains an outward pressure. In the red giant, the core hydrogen is exhausted. The shell fusion causes the outer layers to cool and expand. The helium flash is when the helium ignites in the core. With a sudden energy release, the core expands and the outer layers shrink. The planetary nebula occurs when the fusion ends, the outer layers are expelled, revealing a hot inert core. And the white dwarf is where there's no fusion and the star is slowly cooling over time via radiation loss, supported by electron degeneracy pressure. pressure. Now the star does not get hotter and brighter at every stage. The red giant is cooler but brighter. The white dwarf is hotter than the red giant but dimmer due to its small surface area. The brightness depends on the temperature and the surface area. So this statement is inaccurate. Whilst energy processes continue, the star's apparent brightness and temperature change non-linearly during its evolution. A group of astronomers is studying stars in a globular cluster. They observe the absolute magnitude and surface temperature of 30 stars within a small region of the cluster. This data is plotted on a simplified Hertzsprung-Russell diagram plot, as described on the screen. A student suggests this cluster must be older than the Sun, since it has red giants but no Sun-like main sequence stars left. Describe the general structure of the Hertzsprung-Russell diagram and explain what determines the position of a star on it. Using the distribution of the star in the cluster, explain what can be inferred about the age and past stellar evolution of the cluster. Evaluate the student's conclusion that the cluster must be older than the Sun. In your answer, consider how the absence of Sun-like stars and presence of giants and white dwarfs support or challenge this view. So pause the video now, then unpause the video when you want to go through your answer. Right, the Hertzsprung-Russell diagram plots luminosity at absolute magnitude against surface temperature or spectral class. The temperature decreases from left to right, and the luminosity increases from bottom to top. Stars on the main sequence fuse hydrogen in their cores. Their position is determined by their mass and temperature. Giants are bright and cool due to the large surface area. White dwarfs are hot and faint due to their small size. The absence of hot massive stars implies they've already evolved off the main sequence, so these stars have a short lifespan. The presence of red giants indicates intermediate mass stars have left the main sequence and are undergoing helium fusion or shell fusion. The white dwarfs indicate that some stars have completed their life cycle, supporting an older population. The dominance of cool, faint main sequence stars imply only the low mass stars remain on the main sequence. These features all collectively indicate the cluster is much older than a few billion years, so likely older than the Sun. Now, the student's claim is supported by the data. The absence of Sun-like stars indicates they've already evolved off the main sequence. The Sun is about 4.6 billion years old, in a cluster with no similar stars on the main sequence, so stellar evolution must have progressed further. The presence of red giants and white dwarfs indicates the more massive stars have completed their main sequence lifetimes. However, the Sun's position may not be visible due to observational limits, so the conclusion must be cautious. So the conclusion is reasonable, but relies on assuming the survey is representative and fully complete. A research observatory studies the aftermath of a supernova, detects two compact remnants in different parts of the sky. Object A has a radius of 12 kilometers and a mass of 2.1 solar masses. Object B has a mass of 3.4 solar masses but no visible radius detected. A short gamma ray burst lasting 2 seconds is also observed shortly after the collapse of Object B's progenitor star. The team aims to classify each object and determine the nature of the energy released involved in the GRB. Explain how the escape velocity from the stellar remnant determines whether it's classified as a black hole. Use the Schwarzschild radius formula to determine whether Object B could be a black hole. Then discuss how the extreme density of Object A affects the atomic and subatomic structure of matter. In your answer, refer to the internal structure of neutron stars. Then evaluate the evidence that Object B produced the observed gamma ray burst. In your answer, consider timing, mass and energy scale involved. So pause the video now, then unpause the video when you want to go through your answer. Escape velocity is the minimum speed needed to escape the gravitational field of an object. For a black hole, the escape velocity is at or within the Schwarzschild radius exceeds the speed of light. If no radiation escapes, including light, the object is a black hole. When we work out the mass of object A by converting our solar masses into masses in kilogram, we can say the Schwarzschild radius is 2 gm over c squared, which is 6.2 kilometers. Now the actual radius is 12 kilometers, which is larger than the Schwarzschild radius, so object A cannot be a black hole. It is in fact a neutron star. Now, neutron stars are composed entirely of neutrons with densities exceeding the atomic nuclei. Electrons and protons are forced together to form neutrons in the collapsed core. The electron degeneracy pressure fails, the neutron degeneracy pressure takes over, matter exists in a degenerative state with quantized energy levels tightly packed in. Now, the extreme density prevents atoms from existing in their normal form, so it behaves like a giant atomic nucleus. Now, GRBs last under 2 seconds are believed to arise from the collapse of massive stars or mergers, so it's likely as the formation of a black hole. Now, object B is more massive, so it will collapse into a black hole. Now, the timing and absence of a visible remnant suggests that it was linked to GRB, which is consistent with a sudden gravitational collapse. A team of astronomers studied a binary star system where one star, star A, undergoes a Type 2 supernova, leaving behind a compact object while the companion star, star B, is unaffected. Prior to collapse, star A has a mass of 12 solar masses. After the supernova, a remnant with mass 2.4 solar masses is detected. It emits strong X-rays and exhibits periodic pulses every 1.3 seconds. The team records a sudden ejection of material and calculates the energy released during the collapse to be approximately 2 times 10 to 46 joules. They also observe gravitational disturbances in the system, indicating a loss of mass during the explosion. Explain how a Type 2 supernova differs from a Type 1A supernova, both in observation and in origin. Using remnant mass and pulse behavior, identify the nature of the compact object and justify your reasoning. The team wants to estimate the energy released during the collapse and see if it's reasonable. Calculate the gravitational potential energy released if the remnant collapsed from a radius of 10,000 km to 12 km using the formula on the screen. Evaluate whether the collapse energy calculated in 1.3 supports the astronomer's measured value of 2 times 10 to 46 joules. Consider assumptions and limitations of the model. So pause the video now and then unpause the video when you want to go through your answer. In our first one, Type 2 supernovas are a core collapse of a massive star, which leaves a neutron star or a black hole. Type 1A supernovas is the explosion of a white dwarf that accretes mass from a companion until it reaches the Chandrasekhar limit. Now, Type 2 shows hydrogen lines in a spectrum. Type 1A does not. Now, Type 1A has a consistent peak brightness, so it uses a standard candle, whilst Type 2 varies a lot more. Now we convert our mass of 2.4 solar masses, and we know it's much above that white dwarf limit of 1.4 solar masses. It emits pulses every 1.3 seconds, indicating a rotating neutron star or pulsar. The radius of the 12 kilometers is consistent with a neutron star, so therefore the remnant must be a neutron star. It can't be a black hole, doesn't have enough masses, and is given off pulses of radiation. We then sub the values into the formula given on the screen. Now we've got to convert our mass from solar masses into kilograms. We then estimate all our values and we get our answer to be when you work it through, to be 2 times 10 to 46 joules, which is consistent with our measured value. Now finally, the model assumes uniform spherical mass distribution, which is a simplification. The actual collapse involves energy loss via neutrinos and kinetic energy of ejected material, so it won't all go into observed electromagnetic radiation. However, the agreement does support that the observed energy scale is reasonable, despite the uncertainties in the actual collapse that does take place. So thank you for watching this revision session today on AQA A-Level Physics. If we've learned in today's revision session, we can answer A-Level Physics exam style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So thank you so much for watching this revision session on paper 3 for AQA A-Level Physics in the option of Astrophysics, looking at the topic of stars. Thank you so much and have a lovely day.